Hello everybody, my name is Chinita Henderson and today I'm going to be teaching you the zeroth, first, and second order of reactions. So what this is it's in chemistry, specifically kinetics. Kinetics is the rate of a reaction or the speed. So with rate, that's basically an equation that shows how fast it's going as well as the concentration of its chemicals and how they change. So first we're going to just go over real quick the rate law, just in general. That way we know what order reaction we are working with. So the rate law, let's see, equals the concentration of A, which is the first chemical, to the power of N, and then the concentration of the chemical to the power of N. So this is the general rate law. Now, when you are calculating what order it is, you're going to take the M and the N, you add them together, and this will tell you what number your order reaction is. So it'll look something like that. I don't know if you can see. So now we're at this point. So for example, if we had one that the chemical A had a power of 1, so an order of 1, and then B had an order of 2, the overall rate law would be 1 and 2. So you would add these together and you get third order. So you can either do it individually to get the order of a specific chemical, or you could do the overall and you would add these together. Now for a second example, if you were to have two different rates that were done experimentally, so if you had rate, let's say 2 divided by rate 1, and these values were equal to molarity to the power of M, and then 0.30 molarity to the power of N, all over K molarity 0.6 M over 0.10 molarity of N. So at this point, let me see if you can see it. Okay. You could cancel out the numerator and denominators, so these two would go out. So you'd be left with these two. Okay, so now at this point you would just divide these two, so you would get 3, and then it would be equal to 3n, n would equal 1. Just as an example to find n. Now if you did the same kind of thing for m, so let's do a little simpler one here. Over K, molarity A, and molarity B, and so for m, it would go more like this. And then you would get your number, which is equal to this number to the power of m. M equals that number. Then these two, let me see if you can see. Okay, perfect. Then these two you would add together for your overall rate. So these two you would combine together for your overall order. So it kind of looks something like that. So now that we know what number or order reaction we have to differentiate which rate laws, which integrated rate laws, and which half-life equation to use depending on what order it is. So I'll be going over the 0th order, 1st order, and 2nd order, and which equations and graphs pertain to which order. All right, I just went ahead and drew it up real quick. So this is what it would look like for the 0th, 1st, and 2nd orders. This would be the respective rate law. The top, middle is the integrated rate law, and the bottom would be the half-life. And also, just as a general thing, K for us in this instance, lowercase k, usually for me I'll put a underline if it's the capital K, but that is for equilibrium, so we want to make sure we can differentiate if it's lowercase or capital. All right, K is the rate constant. So K here is our rate constant. In chemistry, that means that it is the constant factor which indicates the speed of reaction under certain conditions. The value of K is determined experimentally and is independent of the concentration of the chemicals and the reactions, but it can change depending on the temperature or things like surface area, volume, things like that. So first, I'm just going to write the rate laws for the 0th, 1st, and 2nd order. So for a 0th order reaction, the rate is going to be equal to the rate constant down here. What that means is basically once you calculate the rate constant, it would be equal to that. For a 1st order reaction, the rate will be equal to the rate constant times the concentration of your chemical. In this case, it would be chemical A. And then for the 2nd order reaction, the rate will be equal to your rate constant times the concentration of your chemical, and then just square it. So those are going to be the respective rate law to the 0th, 1st, and 2nd order reactions. Now we're going to move on to the integrated rate law. So for the 0th order integrated rate law, the concentration of A is going to be equal to your rate constant times the time that it took. So we're also going to be doing the charts or the graphs to see what the lines would look like as well. For our integrated rate law for the 1st order reaction, we're going to take the natural logarithm of the concentration of A, equal it out to the negative rate constant times the time, plus natural logarithm of the concentration of A. Now for our integrated rate law of our 2nd order reaction, you're going to take 1 over the concentration of A, equal it out to the rate constant times the time, plus 1 over the initial concentration of A. So with the initial concentration, let me do black. Initial concentration of A would have this little 0 here. What this means is that the time is at 0. That's just a little way that I like to remember it because sometimes it gets a little confusing when you see these little dots. But you just have to remember if it has a little 0 there, the time is at 0. So on a graph, you see the x-axis is time. Somewhere here would be the initial concentration. That's basically what that looks like. So that part concludes our integrated rate law of the 0th, 1st, and 2nd order reactions. Now we're going to move on to the half-life, so T1/2 of all 3 of these. So for our half-life of a 0th order reaction, you're going to get T1/2 or half-life equals initial concentration of chemical A divided by 2 times the rate constant. For the half-life for a 1st order reaction, the half-life is going to be equal to 0.693 divided by the rate constant. So this one is a constant factor, so this number does not change. And then for our last half-life here, for the 2nd order, the half-life would be equal to 1 divided by the initial concentration of A times the rate constant. So here is our chart of the 0th, 1st, and 2nd order reactions for the rate laws, integrated rate laws, and the half-life. So I'm just going to erase this down here, and then I will show you what the lines will look like on a graph. Alright, so here I made some graphs for the 0th, 1st, and 2nd order of the graphs. And in this one, I'm going to do time on the x-axis and concentration on the y. So we will see how the reactants, the initial concentration of A, how they're going to change when time goes by. So it can be them reacting with another one and being consumed, and then the products would be getting formed, so it would kind of look like the opposite. So the first graphs I'm going to be doing is going to be time versus concentration of the chemical A. and I'll be doing that for the 0th, first, and second order reactions. So starting with the 0th order, this one is going to be the concentration of A. So you're going to find where your initial concentration is. So you're going to find where your initial concentration is. And with the 0th order, it's going to be linear, meaning it's going to be a straight line. So with the first order reaction, it's going to be the natural logarithm of A. So you'd also find your initial starting point. This one's going to be a little more curved than this one. So there's a little bit of a difference there. Our last graph here is going to be equal to 1 over the concentration of A. So again, starting here, this one is going to have a steep drop and then level out. So this is how you can tell if it's 0th, first, or second, if it is the time against concentration, linear, slightly curved, and then huge drop. So now on to our next charts. This is going to be the concentration of A against the rate of the reaction. So we're going to do this for the 0th, first, and second order again. So in our 0th order reaction, our rate is going to be equal to our rate constant. So what that's going to look like is a straight line all the way across. For our first order reaction, it's going to be rate equals rate constant against the concentration of A. So it's going to start at 0, and then it's going to do a linear line straight up. So with this, our slope would equal the rate constant. Lastly, for our second order reaction, it's going to be rate equals the rate constant times the concentration of A squared. This one isn't going to be linear, it's going to have more of a curve to it. So it'll be like that. So for our second order, it's going to have more of a curved slope like this. And then this one is going to be equal to 2K concentration of A. That's going to be the slope right there for that. So we've now gone over the rate law for the 0th, first, and second order reactions, integrated rate law for 0th, first, and order reactions, and half-life of 0th, first, and second order reactions. We've also gone over 2 different types of graphs. One is going to be the time against concentration, and then this one is going to be concentration against the rate. So when you're doing 0th, first, and order reaction graphs, it's important to pay attention to the names of the x and the y-axis, as this one could be time or it could be concentration, whereas this one could be rate or it could be concentration. And that's going to give you a different equation here and a different line of what you're looking for. So that concludes the video. I hope you have a great rest of your day, and thank you for watching. Bye-bye.